Okay, question 6c and 7 now. Going back to question 6c. One point with this arrangement is the oscillations of the sphere occur when the switch is closed. Show the period of oscillations is about 0.6. Second, simple equation for the time period of a mass spring system. We know the mass is 1.5 times 10 to the minus 3, and we know the spring constant is 0.18, gives us 0.57 seconds. Part 2 of that, it says in practice the oscillations are damped. Sketch a graph showing how the amplitude of the oscillations changes with time for the damped oscillation. Now it's worth talking about this a fair bit because this is a 5-mark question, and I can't imagine this bit being worth more than 1 mark because it's a piece of cake. So somehow this is probably 4 marks, at least 3. So I'm assuming we want to label our axes, which I haven't done. So this would be x, period, the displacement, and this would be time. Maybe put some units on there, something like that. You then want to basically just try and give yourself some guidelines. I've just dotted over my green pen here to show something approximating exponential decay. You don't have to be too crazy about it, it's a sketch after all. Then what I've done is I've gone in and I've just tried to put in a bunch of, to the best of my, I don't even have a rule with me now, but the best of my ability, uniformly spaced out time markings. Okay, now we know the period of oscillation is going to be constant, so the time for a quarter oscillation must be the same. Okay, and then what you want to do is just try to get it to sort of touch your guidelines at the point. So I haven't really done a very good job of this, but I'm thinking that's what they're going to be looking for. What it's very easy to do when you sketch something like this is to show the time period changing. So you're going to be wanting to show that the time period is constant. You want to show exponential decay. Yeah, I suppose. I'm guessing you want to label your axes, and I can't really think about what else it could be. But anyway, that's all I can tell you about this. Okay, hopefully that is straightforward enough. Maybe this was a 2-mark question, I don't know. Anyway, let's crack on. Question 7 says to us, shows you this bit of a picture of a graph in here, which I think you can see. I don't have graph paper, like I said, I don't even have a ruler at the moment. So it does tell you that the radius of the Earth is 6.4 kilometres, you know that. So if I've sketched my graph, and you can read from this graph they give you in the book that is 84 newtons per coulomb, the field strength at that point. So I know straight away up there I can put my point there for 84 newtons per coulomb. It then says determine the electric field strength at B, which is, if you look on the graph, is double the radius. It's if that's 6,400, this would be 12,800 kilometres out. Now, if the field strength is given by E equals Q over R squared times by this constant, then obviously this is, field strength is inversely proportional to R squared. So doubling the R should quarter the field strength. Therefore, we can plot our point here at 12,821 newtons per coulomb. Okay, so that gives us that. And then it says show determine the field strength at B, and then complete the graph to show how the field strength varies with distances from the centre of the Earth for distances greater than 6,400. Now, obviously, I just thought, we know it's going to be an exponential curve, we know it's not going to touch the line. I just thought I just extended my line a little bit to roughly work out where it would be if I doubled it again, and then put that as being roughly a quarter, but that's possibly a bit unnecessary. So we've got this exponential curve that doesn't touch the line. State how you would use the graph to find the electric potential difference between points A and B. Now, this is quite interesting. I have to think about this for a bit, because what you get is, well, if the field strength E is equal to Q over R squared times by R constant, and V is equal to Q over R times by R constant, that's potential, then it stands to reason that E times by R, if you times E by R, you just get rid of the R squared factor. Okay, and of course that is the same as potential. So E times by R is potential. So if you think about that, what that basically means is that area, if I want to know what the potential at A was, it would be all of the area under the graph if I went from infinity to A. This whole area under here would be the potential at that point. If I want to know what the potential was at B, it would be the area under the line if I went from infinity all the way to B. Therefore, the potential difference between these 2 points would be the difference in the area under the line of both of them from infinity, which would essentially be the area under the line, which is made out between these 2 points here. So this area under the line between A and B is the potential difference between A and B. Okay, hopefully that makes sense. B tells us to calculate the charge on the Earth. That's relatively straightforward. We've got the field strength, we know the equation of field strength, we've got the numbers, we just simply rearrange, make Q the subject, and bang in values, and we get 3.83 times 10 to the 5 coulombs. Part 2, the charge is distributed evenly over the Earth's surface. Calculate the charge per square metre on the Earth. So the area of the surface of a sphere is 4 pi r squared. Therefore the charge per area will be the charge we got there divided by 4 pi times the radius of the Earth squared. And that gives us 7.4 times 10 to the minus 10 coulombs per metre. Right, that's that. That's the end of the questions for chapter 5, electric fields. You guys now need to read all of chapter 6 and do summary questions 1 and 2 for each of the bits, and the end of chapter questions, I think. I can't remember what I told you, but it's in my book. Anyway, good luck with your homework. Have a good half term. Cheers.